Thank you very much, Ani. Thanks to all of the organizers and for the invitation, and also thanks to IPAM. I really appreciate this opportunity. I think Connie basically laid out exactly what I'm going to talk about, with a specific emphasis on how, or I guess why and how we're going to use mobility on-demand fleet models to help answer policy questions and to really ultimately to optimize policies in particular the state of California, but ultimately across MPOs in the country. So I'm going to be discussing two different projects today. The one is for the most part completed, funded by Irvine National Labs with a number of my graduate students and a postdoc at UCI, along with colleagues at Irvine National Labs. And the second project is an ongoing one, and it's actually a planning grant with, again, my more senior colleagues at UCI and with SANDAG, the MPO in San Diego. This is a NSF project. Okay, so the agenda for today will be giving some background on transportation system simulation modeling software, and then mobility on demand fleet modeling. We heard a lot about this on definitely Wednesday, but even some Tuesday as well. I'll also kind of provide some context for why I think it's important to get high quality, high fidelity MOD models into regional planning models. And then lastly, I'll talk about some computational analysis and results associated with particularly the trade-off between computational efficiency and fleet performance for large-scale simulations. Okay, so what are transportation system simulation models? I have a list here on the right-hand side of 3 open source software, as well as some work I did with my advisor and a number of other colleagues at Northwestern, that's Hani, kind of integrating CT ramp activity-based models with Dynasmart dynamic traffic assignment and NUTrans, our dynamic traffic assignment, transit assignment simulation software. So the main characteristics of the simulation models and software are synthetic populations that are agent-based. This includes things like the sociodemographic information of the synthetic population, how many vehicles each household and individual owns and has access to, the home and work locations of these people in a geographical region, and ultimately some of the activities that they have to complete or should complete either in a day, a morning peak period, or even across an entire week. It's also good models have both the demand side and the supply side. There's trip-based models, but mainly activity-based models now currently in the more advanced software. Activity-based modeling is not my area of expertise, but I am working to integrate my models into activity-based travel demand models. So these purpose are to determine activity locations and what time these activities should occur, as well as mode choice for individual trips, but also tours. And one of the advancements of activity-based models is thinking at the tour level or the trip chain level. And then dynamic network assignment simulation models are ultimately concerned with route choice, and some of them are concerned with departure time choice in a network in which congestion is endogenous. So the question is why? So why use simulation software when there's this entire literature of analytical models that are out there to help model transportation systems? I think there's a long list, but a couple things I want to point out is to model the complexities of travel behavior and the transportation network congestion at scale. And ultimately to provide useful insights to transportation decision makers. Some things here, forecasting future scenarios, depending on certain inputs that you might assume about the future, sociodemographics, population growth, land use patterns, etc. Can also analyze infrastructure investments, large scale, out into the future infrastructure investments, as well as analyzing potential regulations and both transportation and land use regulations. And I'll discuss some examples of those in a couple slides. So the benefits of simulation models compared to analytical models include high fidelity, high resolution. It's relatively easy to provide detailed models of how individual agents might react to external stimulus. There's also, compared to most of the analytical models, extensions and integrations can be somewhat straightforward. At least from a computational perspective, you're not so worried about making sure that your new constraint is convex rather than non-convex. However, that's not to say that it's straightforward to behaviorally integrate these models. That's a really hard challenge and something that we're all thinking about a lot of the time. Simulation models also tend to be more policy sensitive to a wider range of policies. And one thing that's, for me as a researcher, is quite valuable is the large volume of output. So if you think about modeling an entire transportation system, you can get information about links, you can get information about the systems level, about individual agents, about different regions of the system. Kind of any type of output you want, you can get it from an agent-based simulation model. So the disadvantages are that they're highly data intensive. Calibration and validation can be very difficult, if not impossible in some cases, particularly when you're simulating future scenarios that don't exist right now. And then theoretical guarantees around the quality of a solution basically are non-existent, particularly in large-scale detailed simulation models. About mostly today is the addition of a new model or component to transportation system simulation models, and that's mobility on demand services. So you can think about this as the types of services that Uber and Lyft are operating. And what I'll be focusing on is kind of a future scenario in which there's driverless Uber and Lyft type fleets. But that can be extended to handle things like dynamic ride sharing or micro transit fleets as well. And from a kind of engineering problem perspective or operations research problem perspective, ultimately these are dynamic dollar-ride problems with kind of 4 key sub-components or sub-problems. There's the matching or assignment problem between vehicles and travelers. There's the routing and scheduling of the vehicles through the network. And there's also the repositioning of the vehicles to be prepared for future demands. So I'm going to kind of provide a background now, talking about an ongoing study or planning grant from NSF called Addressing Unprecedented Community-Centered Transportation Infrastructure Needs and Policies for Mobility Revolution. So this is ultimately the questions that we want to answer, and then I'll follow up by discussing how we're going to do that by way of integrating these mobility on demand models into broader transportation system simulation software. So the project goal is pretty straightforward and pretty wide-reaching: to improve sustainability, livability, and mobility through decision support at the regional or city level, support related to infrastructure upgrades for connected automated vehicles, mobility service providers, as well as policies and regulations surrounding those technologies and those services. And we're going to specifically focus on these new innovations, so mobility services and connected automated vehicles. So the problem statement, and this actually comes from the way NSF and the Smart and Connected Communities grant asks for the problem statement, which I think is really nice for researchers to think about from 2 perspectives. What's the societal problem you're trying to address? And ultimately, what's the technological challenge that you're also going to address? From a societal perspective, at least the way I see it, the viability of both mobility service providers and connected automated vehicles is uncertain. I mean, I would say they're both going to exist in the future, but how we get there and what their market shares are uncertain. This uncertainty is coming from a financial perspective. If you look at Uber and Lyft's balance sheets over the past quarter or past year and a half, doesn't look great in some ways, but of course, if you look at their valuation, it looks really good. From a technological perspective, there are certainly challenges that connected automated vehicles developers have to address. And then from a political perspective, there's questions as to how the constituents of cities are going to react to these new technologies and new services. And I also think there's a need for planning and regulation related to mobility service providers and automated vehicles in order to obtain their potentially huge societal benefits while avoiding some of the pitfalls. So from a technological standpoint, the existing transportation regional planning models, at least in the States, do not have sophisticated models of mobility service providers embedded in them. That's a real kind of gap in practice and to a lesser extent the literature. And then another thing I'm going to be talking about here is optimizing transportation policies and infrastructure decisions. So the existing regional planning models are mainly for evaluation purposes. You just somewhat, I wouldn't say arbitrarily, but you take potential policy ideas from either the state or the federal government or a number of constituents in your areas, and you test whether or not those policies are going to be effective with your regional planning model. But what if we could embed on top of our evaluation model an optimization model that tries to broadly meet these societal goals that I mentioned earlier: sustainability, accessibility, mobility, etc. And we're really ultimately optimizing for community outcomes, not necessarily for just increasing the number of CAVs on the road or increasing the market share of mobility service providers. So I'm going to, in the next two slides, going to go over pretty simplistic, but I think powerful models of the old transportation system and the new transportation system. So this model right here, this conceptual framework, lays out two key decision makers. At the bottom are the travelers. That's you and I who are making decisions on routes, modes, departure time choices, our use of the transportation infrastructure. And then the black box here says transportation infrastructure managers, but it's about as broad as you can think in terms of the public sector and the decisions it makes related to our transportation system. So that's new lanes, that's existing lanes, maintaining, rehabilitation. It's also transit agencies, bus lines, bus stops. It's the cyber physical infrastructure as well, communications, technologies, tolls, all of the above. So the way I see it, we're moving towards a new transportation system that has a third player, which is the private sector entities, that is the mobility service providers. And in this case, we'll be talking about them owning connected automated vehicle fleets and operating those connected automated vehicle fleets. But even now, without fully connected automated vehicles, these mobility service providers are playing a key role. So they're, as I like to say, demanding transportation infrastructure and supplying mobility to travelers. Travelers are still getting some mobility directly from the transportation infrastructure, but they can also acquire mobility from mobility service providers. And these mobility service providers are making important decisions related to their service designs. How much sharing should we allow? What types of reservations? Fleet size? Is it going to be a door-to-door service or pick-up drop-off points? They're also even making important decisions related to their vehicle design, particularly in the case of connected automated vehicles. We're going to have small vehicles, one-seater, two-seater vehicles, or 10, 12-seater vehicles. Of course, the answer is we're going to have all of those, but to what extent will each of them show up in the market in the future? So I won't get into this too much today, but ultimately I think it's the key potential contribution of this going forward. So on the right-hand side, I have a bi-level optimization model. And on the left-hand side, I have kind of, let's call it the state-of-the-art of regional transportation planning models. High-resolution, data-intensive, activity-based travel demand, dynamic network assignment simulation models. So that's, again, very high-resolution, high-data-intensive. That tends to be used to evaluate policies, but not make policy decisions. So the right-hand side is a bi-level optimization model, with the upper level being infrastructure upgrades, or more broadly, policy decisions. So that could even include regulations. That feeds to a lower level response model I'm labeling here a simple analytical model of travel demand and transport supply. There's been some work even from Samita's group using Bayesian optimization for this type of bi-level approach. Similarly with Carolina Osoria's work at MIT, using simulation optimization to address that. But I think the integration between the left-hand side and the right-hand side is another key way in which this is going to be a major contribution. So we're going to test the output of the bi-level model on the simulation on the left-hand side. We're also going to use that simulation model to calibrate simple analytical models. So this is a fully integrated approach. And the research questions we're trying to address here are, how are currently Uber and Lyft impacting the transportation system? And what policies and infrastructure investments in the future can be made in order to improve the entire system from a sustainability, accessibility, and mobility perspective? And we're also interested in the deployment timeframe for infrastructure decisions. So when should you be making upgrades on particular links in your network to support connected automated vehicles, given all the other kind of things that are pulling on planning agencies and decision makers? Okay, so that's the big picture. Now I'm going to kind of dig deep into the actual integration of my mobility on demand fleet models that I developed during my dissertation work at Northwestern into some of these transportation system simulation models. And ultimately, it's a balancing act between computational efficiency and modeling how I see future automated mobility on demand providers really pushing the limits of fleet performance. So very briefly here, automated mobility on demand is a fleet of driverless vehicles providing transportation service to individual people or groups of people. We assume the fleet's controlled by a single entity. That entity is centrally controlling the fleet. We assume they own the fleet, and that, at least in the case of the United States, these fleets will be owned and operated by private companies. That's the way it looks right now, at least. So some examples are Waymo in Arizona, Chandler, Arizona. They had a fleet of 10 fully driverless vehicles. It seems they're expanding the size of the fully driverless fleet and now allowing kind of the general population in Arizona to use that fleet. Also mentioned Hyundai and Pony AI, who are operating a self-driving fleet in Irvine here. We've done some work with them. It's not a fully driverless fleet. Ultimately, they plan to take the backup driver and the other person they have in the vehicle out, so that should it's economically efficient. For right now, they're just testing. And what I'll be focusing on is the following service definition. The traveler is requesting rides dynamically via a mobile application. That's their origin, their destination, and then I guess implicitly their request time. The travelers want to be served immediately. They're being transported directly from their origin to their destination. That is, there's no detours to pick up or drop off other travelers, but of course that's an extension that can be made in the future. We're assuming the fleet is functionally homogeneous. The fleet size is fixed in the short term, and we assume the fleet operator has complete control over all the automated vehicles. Okay, so some background. I'm gonna now kind of lay out a dichotomy between the existing literature in terms of what the focus has been. So there's been, I would call, significant and major research on optimal dispatching of mobility on demand AMOD vehicle fleets. This has really been pushing the limits of minimizing wait time, minimizing the number of empty vehicle fleet miles, maximizing utilization of the fleet. So there's been some optimization-based approaches, including some of my own, as well as some work at ETH Zurich and MIT. There's been a bit of work on reinforcement learning and multi-agent reinforcement learning to address this problem in the computer science literature, as well as some approaches using approximate dynamic programming coming out of Princeton. There's been a second string of research that has focused on what I would call relatively simple and straightforward models of an AMOD fleet that have actually integrated them into these agent-based transportation system simulation software. They're quite computationally scalable because of the simplicity of the MOD fleet model that underlies it. So some nearest neighbor approaches, smart nearest neighbor approaches, and zone partitioning. But none of these involve optimization or advanced reinforcement learning or approximate dynamic programming techniques. So the research problem here is the need to model what I would say realistically an AMOD fleet with high quality dispatching policy within these agent-based transportation simulation models. So there's this dichotomy I laid out in the last two slides. There's computationally efficient but operationally ineffective policies. They tend to have much higher wait times and many more empty fleet miles or ratio of empty fleet miles to total miles. And then there's this other stream of research that is somewhat computationally inefficient. So, I mean, ultimately you can scale this if you have supercomputers and you make some simplifying assumptions about your models when you bring them down to the real world. But operationally, these are quite effective. So the objective is to develop a fleet dispatching policy that's computationally efficient, can handle very large fleet sizes in a dynamic network model, and operationally effective enough to at least mimic a real-world AMOD fleet in the future. So the problem components associated with AMODs are the assignment and matching of requests to automated vehicles, to the routing and scheduling of vehicles to pick up and drop off requests, and the repositioning of AVs to balance supply with the future demand. So as far as I see it, routing and scheduling is really not an issue in the case of this particular case because there's no ride sharing. Basically, that is, once you've assigned a vehicle to a request, you already know which route it's going to go on and the schedule it's going to arrive to pick up the passenger and drop off the passenger. So we don't really need to address that. Another quick comment here is that these three components can be integrated, and I have actually done that in some of my work. But today I'll focus just on the assignment problem, but it's just the matching of vehicles to requests. Okay, so the problem statement here, or the engineering problem, is the dynamic assignment problem. So when you see this visually on the right-hand side, you have a set of vehicles and a set of requests. I have 5 and 5 here, but it's more likely to be 2,000 and 1,500. It doesn't have to be balanced, and it's going to be much bigger. So you're given a set of requests P and a set of available vehicles V in your current time step. So this is either the current time step of your simulation or the current time in the real world. And the objective is to assign these open requests to vehicles in real time, both effectively and computationally efficiently. We have 3 measures of effectiveness: fleet productivity, a proxy for wait time, and the total number of requests served. And then we have a single measure of efficiency, which is the simulation runtime of the agent-based model. But we also have metrics associated with how long it takes to solve each one of these individual matching problems. So the formulation is pretty straightforward. It's the bipartite matching or assignment problem. We're trying to minimize the assignment of requests to vehicles. And I have underlined here this reduced decision space. So what I'm going to talk about in the next 5 slides is how we reduce this decision space such that we can still get high quality matches, but significantly reducing the computation time. So we have this tuple or array C here, which is the combination of feasible matches P and V. We have our vector TC, which is the travel cost for a vehicle V to pick up request P. And then our decision variable is whether or not a particular PV combination is matched. And then we have this parameter M, which is the maximum allowable pickup travel time from V to P, which is just a way of preventing very bad matches even after you've trimmed the decision space. So if the vehicle and traveler are 10 miles apart, we just don't allow that to occur, and this by way of minimizing here. The constraints are straightforward. Each unassigned request can be assigned to at most 1 vehicle, and each vehicle can be assigned to at most 1 request. Okay, so I'm going to go over 4 strategies to reduce the computational complexity, that is to reduce this decision space. So the first is the k-nearest approach, which involves simply looking from a single vehicle to the k request around it, or conversely, which you'll see in step 2, from a request to the k vehicles around it. So given these definitions here of the number of available vehicles, the number of available requests, and our input analyst parameter k, in the unrestricted case, the number of decision variables is V times P, in which case we're considering for matching all vehicles and all requests in the entire region. And under the k nearest vehicles restricted case, our decision space now is k times V. So just, obviously all of you are really good at math, but to see it here with numbers, in the unrestricted case, in the example, we have 7.5 million decision variables, and in the restricted case, we only have 12,500 decision variables, which is a multiple orders of magnitude difference in the size of the decision space. So strategy 2 for reducing computational complexity is just a slight variant on number 1. It's just simply checking whether or not the number of open requests is less than the number of available vehicles, or the reverse case. If the number of requests is less than vehicles, we look from a single request to the k vehicles around it. Otherwise, we look from the from the vehicle to the k request around it. So this has computational benefits. Instead of k times V or k times P, it's the k times minimum of V or P. And it's also, at least empirically, we really don't have a proof of this, of course, the effectiveness of the assignment tends to improve with this hybrid approach. So step 3 is in terms of how we build C. So we're going to try to take advantage of the zonal structure of the region and also the state of each one of the vehicles in the request. So we're keeping track of which region or which zone, which subregion or which zone each of the vehicles in request is in the simulation. So option A, which is the inefficient way, is to build your minimum heap or your priority queue from a single request to all vehicles, and then pop out the k nearest vehicles from that priority queue into a new queue. Option B is to incrementally build your priority queue or your minimum heap zone-wise, taking into account the spatial structure of the region. And again, because the number of vehicles is much greater than k, we have significant computational benefits in terms of building our vector, our tuple C this way. And I'll give an example of exactly how this is done in a couple slides. And finally, the 4th strategy And this really applies when you're modeling this problem with an underlying transportation network. If you're working in Euclidean space or Manhattan space, you don't have to worry about this too much. But when you need to calculate shortest paths between particular nodes in a network or particular links in a network, this fourth strategy here can be quite beneficial. So we have three different options to compute our cost object TC. Option A is very computationally efficient. You just have an offline skim matrix, which gives you an approximation for each zone to each zone in the region, how long it would take for a vehicle to get to a passenger. Option B is in the midst of the simulation, or of course in the midst of the real world, calculating point-to-point travel costs from a vehicle to a request. This can be computationally inefficient. Of course, solving a single shortest path problem is quite quick, but when you're solving it 12,000 times, 100,000 times, 1 million times, the computational kind of time tends to explode. Option C is a preferred approach, which is a hybrid, in which we calculate point-to-point shortest paths when vehicles are near to the request that they potentially could serve. And then when they're far apart, we just use the zonal skim matrix. We just use the offline information. So using point-to-point shortest paths or calculating those for when the vehicles and requests are nearby is very important. So obviously, if the vehicle and the request are in the same zone, your offline estimate would be very, very poor. It'd either be 0 or some aggregate measure you might have. Whereas, if a vehicle has to make a U-turn to turn around and get a passenger based on the current direction it's going, that might actually be a very long time that a skim matrix would do a very poor job of estimating. Okay, so this is an example of how we do that, taking into account the zonal structure. We're going to set k equal to 5 here. We're going to build our k nearest request vehicle heap, and we're going to also calculate our cost matrix TC. So just as an example, we're going to look from 1 passenger to the k equals 5 vehicles around this passenger. So we start by looking in zone 13 where the passenger is. There are no vehicles in zone 13, so we're going to look at the next layer of zones around zone 13. We first looked at zone 7. There's again no vehicles there. We move to zone 8. We see that there are 2 vehicles. We calculate the shortest path from this passenger to vehicle 1 and vehicle 2. We add them to our heap, as well as our measure of the cost for that passenger to get to those 2 vehicles. We move to zone 9, there's no vehicles there. We check zone 14, there's 2 more vehicles. We calculate their shortest path, we add them to our heap and move forward. You can see where this is going. There's nothing in zone 19, nothing in zone 18. We find our 5th vehicle in zone 17. We add it to our heap, and we have now calculated our cost object and the k nearest vehicles around a request. Okay, so what I've just laid out is simply a way to drastically decrease the size of the decision space and also efficiently calculate our cost objects. So I'm going to basically show the computational performance and the vehicle fleet effectiveness metrics associated with that. So we implemented this into Polaris, an agent-based transportation simulation software developed by colleagues at Argonne National Labs. We solved the optimization problem using Cplex. You could also use Gurobi, or even potentially more efficient algorithms you develop yourself. So we did this in the Bloomington, Illinois network. So the base case is a somewhat small fleet size, but we do ramp up the fleet size case. We've also run this in Chicago for tens of thousands of vehicles and hundreds of thousands of requests. I don't have those results right now, but Argonne has them and it's performing quite well. So we have 4 different policies I'm going to compare. Our preferred policy is A3 here, which is using optimization, of course, using the k nearest hybrid approach in order to reduce the decision space. And then in terms of calculating our cost object, we're going to use this hybrid approach with point-to-point travel times and zonal skims. We're going to compare that mainly with A1 and A4. A1 is the existing rule-based zonal policy. You assign passengers to the vehicles that are in their zone. If there aren't vehicles in their zone, you look to the next set of zones. It's a simple policy that, again, computationally inefficient, but operationally ineffective. We're going to also compare with A4, which is our unrestricted assignment case, in which we're considering all vehicles and all requests in each one of the time intervals. And we're also calculating point-to-point shortest paths for all potential combinations of vehicles and travelers. And then A2 is just a slight
10 minutes. You have 10 minutes, Mike. Okay.
Thank you. A2 is a slight deviation from A3. We're still going to use the k-nearest hybrid approach, but instead of using the hybrid point-to-point and zonal, we're just going to use the zonal skims. And then I've already covered the evaluation metrics, but I'll go over them again. Number of total requests assigned over the 24-hour period, average pickup distance for a vehicle and the passenger it's assigned to, which is a proxy for wait time, and then fleet productivity, the proportion of fleet miles in which the vehicles are carrying a passenger, and then finally our measure of computational efficiency is Polaris runtime. So start by comparing A3, our preferred approach, to A4, the unrestricted case. In terms of computational time, it's really not a comparison at all. There's a 98% reduction in Polaris runtime. We do see, however, that there is a 50% increase in average pickup distance when you move from the unrestricted case to the restricted case, which is something we'd like to improve upon going forward. We tend to do better as the size of the fleet grows here. Comparing A3 to the existing policy in Polaris, which is A1, the rule-based policy, we see that there's a 12% increase in the number of assigned travelers over the day and a 40% reduction in average pickup distance, or this is our proxy for wait time. So it's doing quite well there compared to the existing policy. And then comparing A3 to A2, it's a simple trade-off. You get slight increase in computational time by moving from A2 to A3, but you also get a slight increase in performance in wait times and number of travelers served. So the main takeaway here actually is that the unrestricted case does not scale to larger fleet sizes and larger number of requests. So I'm going to show some sensitivity analysis here. We kind of have two x-axis. On the bottom is the number of vehicles, the fleet size, and then also the number of riders. So all the way up to, let's see, I think that's 17.5 thousand on the far right-hand side, number of riders or requests. Our metric here is average pickup distance, our proxy for wait time. We see that A2 and A3, our optimization-based hybrid approaches, are doing much better than A1, the existing zonal-based policy in Polaris. Of course, as the fleet size increases, such that the gap between supply and demand diminishes, that means that also the gap between A1 and A3 also tends to diminish. But of course, an AMOD fleet provider probably would not want to have more vehicles than it needs. So we would most likely be operating more on the left-hand side here, at least in terms of the imbalance between supply and demand. In terms of Polaris runtime, we see that, so just a quick note here, you'll note that the y-axis starts at 900, not at 0. So even though it looks like you're running into some significant issues with A3, it's actually not that bad. And ultimately, we do have some control over this. We can make K smaller or even adjust K as the simulation goes on, depending on the number of vehicles and requests in the system. So while the rule-based policy is more computationally efficient than ours, it's not that big of a gap, at least practically. So, okay, I'm going to conclude now. I have a few minutes left, but I'll leave that for question and answers. So as far as I see it, agent-based transportation simulation models have a lot of benefits, including relative ease of integrating new modeling components, such as the one I've laid out here, an AMOD service fleet model, that somewhat allows for policy analysis, or not somewhat, it does allow for policy analysis related to AMOD service models. Should there be vehicle caps in cities? What happens if you use congestion pricing just on AMOD fleets as opposed to all vehicles? Any type of policy like that. We also find that, at least I find, that model fidelity is important for policy analysis, but computational time also matters. So if you just do the unrestricted case, you can't simulate, as this symposium is named, right? We're trying to do this at scale, and it tends to not scale. In terms of model fidelity, though, if you're comparing our preferred policy to the existing policy in Polaris, the kind of implications of those two policies are significantly different. Ours is showing that, for every vehicle mile traveled, you're getting about 15–20% deadheading miles. Whereas the existing policy is showing that the percentage of deadheading miles is closer to 30–35%. And that's obviously a huge gap that has huge implications for how you might regulate an Uber or Lyft or a Waymo in the future. And then in terms of future work, so as I laid out in the beginning, ultimately we're trying to optimize policy decisions and infrastructure investments using this transportation simulation model for evaluation purposes. We're going to try to use simulation optimization techniques as well as multi-level mathematical programming techniques, again, using the simulation as an evaluation tool. So, thank you very much again, and I'm happy to take questions.